Hello, good afternoon. Good afternoon, everyone. Welcome to our afternoon lesson. This is chemistry. Before you people came in, there is someone who was asking whether we shall look at other branches. I'm looking into that. I hope we shall look at physical chemistry, but that will be, I think, next month. So next month we are likely to look at some physical chemistry. Okay, and that question was from Hillary. So Hillary, next month we are likely to look at physical chemistry. But I need to first get feedback from you to see where you stopped, so that I can also prepare very well. So let's have a prayer. Let's have a prayer. Someone can give us a prayer by show of hand. By show of hands, someone should give us an opening prayer. Yes, Rhoda.
Let somebody thank for gift of life. We thank you, Lord, for the protection as we're going to learn. I pray that may you give the teacher knowledge to teach us well and help us understand. I pray all this through. In Jesus' name I pray. Amen.
Amen. So thank you so much for that prayer. And I think it is time that we should start. Once again, about the issue of having other branches, we shall have physical chemistry. That will be next month. Okay. So today we need to at least look at this inorganic chemistry, and we finish some metals. We are not all that bad. We need to cover like 2 metals, 2 transition metals, then after we can have another branch. It's not always good to leave things in the middle. It's better we first finish. If time allows, then we look at another branch. We look at one topic, we finish it like that, rather than having very many things but which are incomplete. So we are still looking at transition metals. We are looking at the properties of transition metals, and today is our lesson. My name is MUGUMYWA OSWALD, and this is our lesson today, transition metals. And remember, we are sponsored by Edify Uganda. So these are some of the things that we should look at, or should be our targets today. First of all, we need to, by the end of this lesson, to be knowing how to define a transition metal, and also examples. Then we should be able to state and explain general properties of transition metals, and also explain why zinc and scandium are not typical transition metals. So that's what we need to cover today. So let us all aim at that. By the end of this lesson, at least every one of us should be able to do one of the 3 objectives that we have. So we had looked at some of these things, these are transitions. We had looked at others. For many, we had variable oxidation states. We also had formation of catalytic compounds or ions. We also had paramagnetism and so on. So we had looked at some. So this is just a continuation. So today I want us to look at the formation of colored ions or compounds. Formation of colored ions or compounds. So we are saying that most of the transition metals ions are colored, and in aqueous state they appear as hydrated. They appear as hydrated. What do we mean? If you are to remember very well from O level, whenever we would be carrying out some experiments or practicals, there is where we had like copper 2 ions in solution. We said they are blue in color. I hope everyone remembers that. Then again, like iron 3 ions in a solution, they are brown in color. That's when we used to get a reddish brown precipitate. Then iron 2, we say this is a pale green. Then we had, I'm just looking for the common elements we had before. Then we also had zinc, whereby zinc it was giving us a colorless solution. That is whenever you'd add excess ammonia solution. So what do we mean when we say they appear as hydrated? So if I had like the way we are having copper 2 ions in solution, they appear like this. They appear like this. They appear like this. They are being surrounded. The copper 2 ions are surrounded by water molecules. The copper 2 ions are surrounded by water molecules. So if I'm draw the diagram, the structure of copper 2 ions in a solution, it will appear like this. Meaning of the copper central metal ion, then being surrounded by other molecules. Being surrounded by others. My arrows are showing that the copper 2 ion. So that is how it is. So here we have water. Here we also have water. Here we also have water. Then here we also have water. So that is how our copper 2 ions appear in solution. The one I've drawn here. So that is for the case of copper 2 ions. So even the rest, they appear like this. Remember, there are some terms that we haven't studied, but maybe I can just give you a brief some hint on them. Let me first clear this. So let me cover and create some more space. Let me cover and create some more space where I can write. Okay. So if you have to remember when we were starting these transition elements, when I was explaining these properties briefly before we looked at their details, I said that the formula of a complex, the formula of the complex, it is MLN. Then we put this inside. Then we have Z plus or minus. And we also defined, we said that M is the central atom, which is always a metal. At times we can call it an ion. Then also L is the nature. L is the nature of the ligand. We shall look at these things separately. A ligand is, we can say anything attached to the central atom. A ligand is anything, we can say anything attached to the central atom, but we shall look at it. Then N is the number of ligands. The number of ligands attached to the central atom. And we also call it coordination number. Coordination number. Then lastly, our Z, which is negative or positive, it is the overall charge. The overall charge on on the complex, the overall charge on the complex, like that. So that is what I mean. So when we come back, so M is this one, then our L is this one, then N it is this one, then our Z is this one. So take an example. Take an example of the copper that we had, copper 2 ions. Copper 2 ions. Copper 2 ions, which are hydrated, 2 plus. So in this case, if I change the color, the copper is the central atom or the central ion. Then water is the ligand. The water molecules, those are ligands. Then 4, it is the number of ligands. So in this case, we are having 4 water molecules attached to the copper ion. Then the charge is this one, which is 2 plus or plus 2. I hope I'm clear. And some of you might be wondering where we will get the 4. Where we get the 4. So the way we get the 4 under normal, we just get the charge, the overall charge, or the oxidation state of copper. I think that is better. The oxidation state of copper, it is positive 2. It is positive 2. Then we multiply by 2. We multiply by 2. Then we get 4. But we shall look at scenarios where an ion can have more than that, where it undergoes octet expansion. We shall look at that. But as per now, I'm just showing you how these ions or metals are colored. So from there, let's look at some examples. So we are saying that most of the transition metals, ions are colored, and in aqueous state they appear as hydrated. Examples we have here, we have iron 3. So if I may ask, how many ligands, which number are we supposed to be having here? Which number are we supposed to be having here? Anybody who could guess? Anybody? Like the way we have 4 here. So which one do you think can be got from here? Yes. Hey Joshua, I had put up your hand, then after you changed. Okay, John. John.
9.
I beg your pardon. 5.
9.
9. According to John, is saying it is 9. Thank you for trying. John, you can mute yourself. Then, yes, Karim.
That is 6. 6.
Karim is saying 6. Thank you. Anybody else? Okay, thank you so much. So the answer is 6. So we shall just get, this is iron 3. It is red. Iron 3 with 3, we shall get the 3, and then multiply by 2, and then we get 6. So here we are having 6. Even Joshua had said 6. Thank you. So you can see that iron 3 is reddish brown. Then what is the number of the ligands? What is the number of the ligands, or what we called coordination number? What is the number of the ligands? What is the number of the ligands? Because we have, according to what we have only one type of the ligand. Yes, Rhoda. Rhoda. Hey, Rhoda, you've lowered your hand. Should I say you have forgotten? Yes, Karim.
Ligand.
Sorry?
Sorry?
6 ligands.
6 ligands. Thank you. So we are having 6 ligands. The way we have this 6 is now affecting what we have in the brackets. And our ligand is water. And so on. You can see copper 2 blue, then cobalt pink, and this is chrome 3 green, iron 2 pale green, then manganese 2, that is pink. But you shouldn't worry much. We shall look at how we can name these these complexes when we reach there. Yes, Joseph.
Excuse me, teacher. I may beg your pardon on how to get the number of ligands. I'm sorry, I came late.
Okay. So to know the number of ligands, we just need to first know the oxidation state of the metal, of the transition metal involved. For example, like in this case, if I use this first example, we are having iron. We are having iron with water. And remember, we had looked at how we can calculate for the oxidation state. So can someone raise up the hand and you guide me what to do when we are calculating for the oxidation state? Anybody can raise up the hand and you guide me. You will tell me I right. You tell me I write, or I can give you a chance to write on the screen. Let's first calculate for the oxidation state of iron in this case. I'm waiting for the first hand. So to save time, we shall just come and say, let the charge on iron be x. Let's call it x. So we shall come and say, where we have iron, we have one atom, we say x. We say x plus the charge on water. What is the charge on water? That is if at all, if it has a charge. Yes, Joseph. What is the charge on water?
Sorry?
What is the charge on water? What is the charge on water?
I'm seeing 3 plus.
Not a charge as the water molecule, just water alone. This is the overall charge. This charge is on the whole thing. It is on the whole thing.
Plus 1.
So the charge on water, is 0. The water has it is a neutral molecule. 0. Then equaling to overall charge, which is 3. And then we say x when we take the 3. So this would be so we shall find that when you add 0, maybe I should put this. So we say that x and then plus x plus 0. How do we get the 0? It is 6, which is the number of ligands, then times the charge on water, which is 0. We close the brackets, then equals the overall charge, which is positive 3. Then from there we say x plus 6 times 0, that is 0. Then this one is equal to, this one is equal to 3, to positive 3. Meaning that our x is equal to, positive 3. So this is the oxidation state of, of iron. So to get the number of ligands, like I said, you just get the 3. The oxidation state, then times 2, and there we get 6. So that is how we got the 6 here. I hope I'm clear. I don't allow to be left behind. If you have any questions so far, you can raise up your hand. Okay. So these are different examples. These are different examples of ions and how they appear in solution. Once again, still on this, there is no big difference between copper 2 ions, which are written like this, and this one. Okay, this one I can point it here. There is no difference. There is no. All of them are copper 2 ions. Only that this is how they look like in aqueous solution. I remember in O-level around senior 1 there we defined the word aqueous as anything dissolved in water. So this is how these ions appear in aqueous solution. Okay. So let's look at factors that affect the color of transition metals. So I want to see what brings out those different colors. What brings out copper to be blue? What causes the manganese? 1. Presence of unpaired electrons. And here we have to be specific. In the 3D sub-energy level. Presence of unpaired electrons. Take an example. If we have iron, if it has let's say 4s2, then 3d 6. I hope it has 6. So if I'm doing the orbitals, this one is one box because it has only 2. Remember, each box goes contains 2. 3D, it contains a maximum of 10. So we put 1, 2, 3, 4. So let's put our electrons. Here we have 2 on the S. Remember, I said when you're putting electrons, you first put 1. So in the S orbital, we put 1 first, then we add a second. Then the 3D, we have 6. So we have 1. We first put 1, 1. Then these are 3, 4, 5. Now we come back and pair up. Then 6. So when you put them there and you still have a balance, you go back from the beginning. Don't come and add an electron, let's say from here, when this side they are not paired. When these ones are not paired, that would be wrong. Okay, so the presence of these unpaired electrons, the ones which are the ones, the color changes of transition metals. I hope we are on the same page. So that is point number 1, presence of unpaired electrons. Then secondly, nature of the group surrounding the metal ion. Nature of the group surrounding the metal ion. So it depends on the ligand. Yes, please, Joshua.
Instead of the first point of the presence of unpaired electrons, suppose I say that they are less paramagnetic.
When you say less paramagnetic, it means that you are talking about the other property of paramagnetism. But here we are looking at the formation of colored compounds or the formation of colored ions. Is it okay?
Yes, it's okay.
All right. Yeah, yes, Joseph. Joseph. Joseph, I'm waiting for you to talk. Okay, since you have muted yourself, it seems you have changed your mind. So here we are looking at different ligands. For example, we shall find that, let's say, water ligands, they have different colors. Ammonia ligands, they have different colors. We have carbonyl, also different colors. We have sulfates, also different colors. So the nature of the ligand will surely determine also the color of the transition metals. Yes, Joseph, you were asking. Joseph, I don't get your question clearly. Maybe if you can write a full statement. What do you want to be dissolved, or what should be dissolved? So far we have these two factors that affect the color of transition metals. Let's look at the explanation of those points, or those factors. We start with the presence of unpaired electrons. So we say that the unpaired d electrons, remember we said that we deal with the d subshell. The unpaired d electrons in the ion absorb light energy and are temporarily raised to a higher energy level, but these electrons quickly fall back to their stable condition of the lower energy, emitting light energy in the process. I don't know whether you have covered the hydrogen spectrum. Anybody could have covered the hydrogen spectrum, that is in physical chemistry. Joseph, the answer is yes. So I'm asking, could there be anybody who has covered the hydrogen spectrum? Maybe Joseph, I'll give you a chance to talk so that you can put your question clearly, because now you have changed it. I'll give you a chance to talk after. But I'm still asking, could there be anybody who has covered hydrogen spectrum? If not, I'll just give you a hint or something very brief, because it's a full topic. So when we talk of electrons being excited, it means that if I have my levels, this is level 1, maybe level 2, level 3, they keep on reducing, the distance keeps on reducing, and that's maybe we can have this level. So this level, this is why you find that the lines are very close to each other. We call it the continuum. So this is level 1. We can call it ground level. Level 1, 2, 3, 4. So what we mean by electrons absorbing some energy? Assuming that I have an electron here, it is going to get excited to the higher energy level. In other words, it is going to move from the ground level to some other level, which is above the ground level. So it will move to be temporarily excited, then to move up. When it reaches maybe level 4, it loses the energy to keep on going up. So what happens? It will fall back. So it will fall back. It might fall back and fall here on level 1. And another one comes. It comes to level 4. It also falls back, maybe to level 2. So in that process of falling back, they produce some radiations or some light. Remember, light has got the wavelength, and these radiations which are emitted or produced, they have different colors. So the color of the radiation or the energy being produced corresponds to the color of the ion. I hope I'm making some sense. So that's what we meant by saying that these electrons absorb light energy and are temporarily raised to a higher energy level. So when they get the energy, then they get excited to higher energy level, but these electrons quickly fall back. That is after losing that energy to their stable condition of the lower energy, emitting light in the process. Then the wavelength of the light emitted in case of transition metal ions falls in the wave band of the visible light, whereas the most metals, it lies in the ultraviolet range, which is invisible. So here physics comes in. I don't know how many people have covered the light in physics. If there is anybody, you can intervene and you save the situation. But what we mean is that we have just said that these electrons, when they are falling back, they emit some light. So it is this light that comes with its wavelength. It comes with its wavelength of the light emitted in case a transition ion falls in the wave band of the visible light. So when we talk of the visible light, this is where we can determine the color, because this light can be seen. And visible light or wave band, they have different colors. Whereas for most metals, it lies in the ultraviolet range, which is invisible. So that's why we say that some metals are colorless, because the light being emitted, we can't see it. So we conclude and say they are colorless. But in the real sense, they are not. But because we can't see the light, we say they are colorless. So this is what causes the elements, the transition elements or transition ions, to be having different colors. And once again, this is caused by the presence of the 3D subshell, because the electrons which get excited are the ones in the 3D, not in the 4s, but in the 3D. Then we look at a second factor, the nature of the ligands. So the nature of the ligand surrounding the ion affect the color of the ion in that it influences the amount of light absorbed. So we have those ligands which are heavy, and we have those ones which are light. The one which is heavy is likely to absorb less light compared to the one which is smaller. And when I say heavy, I mean the big ones, and when I say light, the small ones. The presence of ligands also causes electron repulsion, which leads to the breaking or splitting of the unpaired d electrons due to groups with significant difference in energy levels. So when these electrons break, then they reduce on the energy, or they add on the energy, and that energy causes also the change in color. Any questions so far? Any questions? Okay. So when you keep quiet, then I assume that everything is okay. I don't want us to pretend as if we're in church and we can't answer. And when you don't ask, you make me look like a preacher. So members, from here we have finished the other factor, the other property, the one we started with, the formation of colored compounds or metals, those transmitters being colored. So now we are going to another property, which is catalytic activity. So this is where these transition metals behave. Transmitters or compounds behave as catalysts. Yeah, the notes are always sent there, only that a few of you check. So yeah, we are going to look at how these transition metals or transition metal compounds behave as catalysts. Anybody who can define the word catalyst? Who can define for us the term catalyst? Let's have Joshua. I'm seeing your hand, but some people might be there saying that is not picking us. So let me first move around. We've not had any lady. We've not had any lady. Winfred. Winfred, what do you think could be the definition of a catalyst? Ladies. This is what we call emancipation, women emancipation. We learned that in CRE in primary or secondary. It was secondary. So it's time that we exercise that, Winfred, and also need to have gender balance. Winfred, it seems Winfred has, I don't know whether she has refused or whether she doesn't know. Saying Arthur, we are trying to get to a lady. You know, God created a man and a woman, so when you don't balance, you might annoy God. So should I assume that someone with ITL A14 plus is a lady or a girl? Let me take the advantage. Okay. ITL A14 plus.
A catalyst
Maybe if I
is
tell us
a
what is your name?
substance that increases. Pardon?
What is your
Okay,
name?
a catalyst is a substance That increases the rate of reaction without changing at the end of the reaction.
Okay, a substance that increases the rate of reaction without taking part in the chemical reaction. But what is your name? What is your name?
Henrietta Hannah.
Johanna. Hannah, maybe let me help you and put for you the name. Don't say I'm a bad teacher. I've put for you the name Hannah. You're welcome. So we say that catalytic activity of transition elements and their compounds is associated with their variable oxidation state. In other words, for a transition element to behave as a catalyst, it must be having variable oxidation states. It must be having more than one oxidation state. That's what we mean by variable oxidation states. They function as catalysts by changing their oxidation states. So we shall find that these transition metals, in some oxidation states, they don't behave as catalysts, but when they change, then they start behaving as catalysts. For example, iron 3 catalyzes the reaction between iodide and peroxide disulfate ion, but iron 2 does not. Iron 2 does not, but iron 3 can catalyze that reaction. Let's look at examples on how those elements or compounds they act as catalysts. So we have vanadium 5 oxide, or what we call vanadium pentaoxide, which is used in contact process. Anybody who can tell us what happens in contact process? Contact process. Hannah, your hand is still up. Should I say you have an answer to this question? Who can tell us what is all about contact process? Hannah, it seems you have the answer. Contact process. Who can tell us? Yes, Akandinda. Let me check.
I think the contact process is used in the extraction of some metals.
Extraction of some metals. Okay, thank you for trying. Another person? We looked at contact process under sulfines compounds. That was in O level. And I think also we looked at it under period 3 elements. That is at A level. Yes, we have a lady. Yes, Deborah.
For the contact process, I believe it's simply the manufacture of sulfuric acid from sulfur dioxide and oxygen, and vanadium pentoxide.
Okay, thank you, Deborah. So that is it. When we talk of contact process, that is the industrial manufacture of sulfuric acid. We continue. Then we have finely divided iron catalyst in the manufacture of ammonia in the Haber process. So here we are using iron, and we have a reason as why it has to be finely divided. Then we have a nickel catalyst, and this is meant for hydrogenation of unsaturated compounds. I hope we use this one in organic chemistry, where we carry out hydrogenation. So now from here, this one marks the end of that property of catalytic activity. Then we got another property I'm saying two hands. Yes, Joshua.
But teacher, why have we not talked about the manganese 4 oxide?
Manganese oxide. No, I was just giving examples. I didn't give all of them.
Okay.
Or maybe you can add because we have very many, but I just picked a few.
Yes.
I just picked a few. But as long as it is a catalyst and it is a compound of transition metal, then
Okay.
it falls under that category.
Yeah.
Okay. So we are now looking at the exhibition of paramagnetism. This is where they behave as magnets, where they are attracted by magnets. So can someone briefly take us through this, because I've already talked about it? Who can take us through this factor here, this property? This is what I talked about from the beginning when we adjusted the lesson. I'm requesting that let's not have only one person. It's as if others, we don't have brains, or we have and they don't work. I believe this is a science class. This is a science class, and there is no excuse. Some people say science combinations are hard. They are what? They are not hard, because you choose what you can manage. Because there are other combinations, but the moment you choose to be in science, then you show that they are not hard. So I want everyone to show me that they made the right choice, and we move together. Yes, John. John, what do you have to say? John, like I've always told you that our lessons are always live on YouTube, and you never know, your future boss or your future girlfriend might be watching. I'll be like, God, this time I crashed. Yes, Henry. Henry, are you talking? Henry. I'm not hearing what you're saying.
I'm saying
Henry, increase on the volume. I don't know whether I'm the only one who is not hearing you.
the number of unpaired electrons proportional to the degree of paramagnetism.
Okay. Henry, I'm sorry. I'm going to mute you because I'm not hearing anything. Let's have Arthur.
Paramagnetism, it is when the transition metal, it has some of the orbitals are not, they are unpaired. Some of them are unpaired. Now these unpaired realign and they are attracted by the external magnetic fields.
Okay, thank you. Joshua, what is your submission?
On this point of paramagnetism,
Yes, please.
I want to explain it by showing you an example of iron.
All right.
In iron.
First wait. Do you know how to share the screen?
Yes, I know how to share the screen.
So can you work it out and you show us? Oh, it's already worked out.
Maybe I explain to you as you write, because it will disturb me a bit.
Okay, fine.
Yes. Now there is iron 3 and iron 2.
So he's saying that there is iron 3.
Yes.
And iron 2.
Yeah, and iron 2. And for iron 3,
Hmm.
it's 3D. It has 5 electrons.
It has 5 electrons.
Yes, it's 3D.
2, 3, 1, 2, 3, 4, 5.
Yeah.
So let me first do the same here so that we can save time.
Yeah.
1, 2, 3, 4, 5.
Yeah.
So this is the 3D. You said it has how many?
It has 5.
It has 5.
And
this
the
one
2 it has 6. The 3D of iron 2 has 6.
has 6.
Yes. So when we are putting the electrons in the 3D of iron 3, we will put all the electrons in 1, 1, 1, 1 up to the end, and all the 5 will fit there.
So we do this.
Yes.
Then we go back.
No, we don't go back because it has 5.
Oh, okay, fine.
On the iron 2, we will do the same with 5, and then we'll go to the very first part, and we put in the 6.
So 2, 3,
4,
5.
5, and then we put in the we go back and put the 6. So paramagnetism, which is the ability of a metal to be attracted by the magnet, it will be according to how many unpaired electrons the element has. And the one which has the most unpaired electrons is the one which is going to be more paramagnetic. And in this case, iron 3 is more paramagnetic than iron 2.
So we go with iron 3.
Yes, that's all I know about paramagnetism.
Okay, thank you so much. I think I have nothing to add there. Let me also hear from, there is someone called HF. Paramagnetism arises because of unpaired electrons in the atoms or ions. These unpaired electrons spin about the axis, generating magnetic moment, which increases the number of unpaired electrons. Okay, so that is what Joshua was demonstrating here. So remember, this is how we can normally tell that we have this number of unpaired electrons and so on. Once again, the more unpaired electrons, then the more paramagnetic the element is. So we are saying that paramagnetism is a tendency of a substance. In this case, it is we are looking at metals to be weakly attracted by a strong magnetic field. Then such substance is said to be paramagnetic, like many of the transition metal compounds. Then we say in the transition metal compounds, paramagnetism is caused by the presence of unpaired electrons in their metal atom, and we are considering the D. We are considering the D, not the S, but the D. The more the number of unpaired electrons, then the stronger the attraction, and vice versa. Then now we have the opposite. This is what we call diamagnetism. Is the tendency of a substance to be weakly repelled. So here we are not being it is not being attracted by, but are repelled by a strong magnetic field. So this is the opposite. So this is the opposite. This is what we are having here. Diamagnetism. It is the opposite of paramagnetism. So that is what we can say about paramagnetism. We go to the second, to another property. another property, which is formation of complexes. So when we're looking at formation of complexes, we shall combine many things. Others we have just looked at them, which shall just be borrowing knowledge from other properties. So we first define the key terms. First of all, we need to define what a metal complex is. We say it is a chemical species in which a metal atom is surrounded by a number of ions. A number of ions, usually anions. So when we talk of anions, we mean negatively charged ions or neutral molecules. So what do we call this number of ions or neutral molecules surrounding the metal complex? What do you think would be the general name? The general name of these ions or molecules surrounding the metal atom. So that is what we called the ligands. So the metal atom is the same as the central atom. Then the number of ions, we call it the coordination number, and the ions themselves, or the molecules, we call them the ligands. The bond formed between the metal atom and each of the surrounding ions or molecules is called a coordinate bond. A coordinate bond. Then let's look at the factors that favor the formation of complexes. First of all, presence of empty or vacant d subshell, which with appropriate energy, which can accommodate electrons from ligands. So these ligands, they have lone pairs of electrons, which need to be accommodated within the empty or vacant d subshell. In other words, if an element doesn't have the d subshell, which is empty or vacant, then we shall not be able to form other complexes. So now we're saying small and high charged ions, okay. Then secondly, the size, or the small size and high charge density of transitional metal ions. I think that is what Nabdu was talking about. The small size and high charge density of transitional metal ions. Why are we saying that they are small? It is because all these elements, the transition elements, all of them, they are in one period. They are in one period. And they keep on increasing on the atomic number, meaning that the size, the atomic size keeps on reducing instead of increasing. So that's why we are saying they have size. And remember that the charge density is always equal to the charge. It is equal to the charge then over the ionic radius. The charge over the ionic radius. So the charge keeps on changing. Remember, when we are moving across a period, we are moving from one group to another. So the charge keeps on increasing. Group 1, let's say group 1, 2, 3. So the charge keeps on increasing, but the ionic radius keeps on reducing. It is because we are having a small size of the atoms or ions. The charge increasing, then that ionic radius reduces. Take an example. If I have a charge of +4 and I have ionic radius of maybe of 0.04, if you calculate, you find that the charge density will be high compared to when we have a high charge and a high or a big ionic radius. We look at the structure. Of transition elements, but time can't allow. It's 3 p.m. and that is when we're supposed to end our lesson. So this is what we shall do. I'm going to send this in your Google Classroom. So you are going to copy the notes of structure of a complex. You also copy the key terms, the ligand, how to define a ligand. Then we have this assignment, a short one. Explain the general characteristics of transition methods, giving examples in each case. So this is the end of the lesson, and as I said at the beginning, we are being sponsored by Edify Uganda. Those are the funders, then connected by Christian Schools Owners Association and implemented by ITAU. So that is our lesson today. I'm going to only allow 2 questions if they are there. 2 questions if they are there. If they are not, then we can have a closing prayer. Thank you for the lesson. Can we have a closing prayer? Closing prayer, yes, Joshua.
Humble yourselves and we pray. Lord Heavenly Father, one thank you for today. One thank you for a lesson you have had. One thank you for the sponsors that are sponsoring these lessons. And we pray that let their efforts not be in vain. Lord Heavenly Father, I pray that you come and bless our teacher who has been with us today. Bless all my classmates whom I've been with, and let everything I've studied here, let it be of more importance. And let everything we have learned stick into our minds until we excel in our final exams. I've prayed in Jesus' name, our Lord.
Amen. So thank you so much and have a lovely afternoon.
You too, teacher.